In the fourth part of this video on inheritance and polymorphism, we will examine some examples of classes that override methods that would otherwise be inherited from object, and introduce the instance of operator and explain when it should be used. We have already made brief reference to the object class in one of the previous parts on this series on inheritance, but now we consider that class in greater detail. The class object is the root of the inheritance hierarchy of all Java classes, so every class is ultimately a subclass of object. It is important to understand that even when a class does not have an explicit extends clause, it is understood that it extends object. So any class without an extends clause is a direct subclass of object. For that reason, all classes inherit all of the methods defined in object. We have already noted that whenever we define a toString method in a class without an extends clause, we are overriding the toString method that would have been inherited from object. We invariably are replacing that method because what it returns is a hash code of the object, which is not particularly useful. Although there are many methods in object that are inherited, one other method that is particularly noteworthy is equals, which performs a shallow comparison of two objects. We mention these two methods in particular because they are ones that are frequently overridden. We will start with a simple example of a class for lengths to illustrate that every class inherits a toString and equals method from object. Lengths are represented in integral feet and inches. The only method that we explicitly define is a constructor to initialize the two instance variables. Next, let's examine what is needed in the main method that will be used to test it. We instantiate two length objects, one that is 1 foot, the other 12 inches. Then we display both objects by calling the inherited toString. Recall that the call to toString happens implicitly whenever objects are concatenated onto strings. We also call the inherited equals method to compare the two objects. Running it, we see that the toString method gives the hexadecimal value for each object, which is the value of its hash code, and the equals method returns false, which we should expect given that they are distinct objects. We discussed overriding in the previous part. Now let's return to it and compare it with overloading. The first point is that overriding is only possible in the context of inheritance, whereas overloading can occur within a single class. First, let's review how they are similar. In both cases, there are more than one method with the same name. It is possible for a method to be both overloaded and overridden. Next, we consider how they are different. With overriding, the method signatures must be the same. Recall that because the signatures are the same, the determination of which method to call must be made at runtime by examining the type of the object. But with overloading, the signatures must be different. For that reason, overloading resolution can be done at compile time. We added several items to our original length class. At the top is a constant containing the number of inches in a foot that we use in one of the methods we added. Naming constants is a recommended practice for two reasons. If the value of the constant ever changes, it only needs to be changed in one place. That is actually a simple instance of a more general rule about why duplicating code is such a bad practice. Admittedly, in this case, the value of that constant is unlikely to ever change. But the second reason still applies, which is that it enhances the readability of the program by making clear what the constant 12 represents. Although we know that all classes inherit a toString and equals method from object, This time we included our own versions. The equals method that we wrote is intended to do both a deep comparison as well as account for the fact that two lengths can be equal without being identical. Notice that equals calls a private method 2 inches. We have added this method for the same reason mentioned above, avoiding the duplication of code since the conversion needs to be done twice. Let's scroll down to examine the 2-string and 2 inches methods that we have just mentioned. Here is the 2-string method that we added to this version. This method gives the caller the option to convert a length into a string in two ways, either with the suffixes ft and in for feet and inches, or using single and double quotes. Note that whenever we wish to include a double quote in a string, we must precede it with the \escape character as a way of distinguishing it from the meta character double quote, which delimits strings, from the actual double quote character. Because 2 inches is intended to be used only internally, we elected to make it private. Next, let's examine our revised main method. We have instantiated two length objects as before, and then output them both with our 2-string method, calling it explicitly this time so we could specify the conversion format, and then calling the equals method to compare them. Next, we again instantiated two length objects as before, but this time we declared the type of the references to be object. Since length is a subclass of object, these assignments require no typecasts. Next, we display the two lengths with the implicit calls to 2-string and display the result of comparing them with the equals method. There are some subtle issues at work here, so this is one where it would be good to pause and predict what the output will be before we run it. In the first case, our 2-string and equals methods were called. Because our equals method not only does a deep comparison, but also accounts for the fact that the lengths can be equal without being identical, the result is true, as we would expect. In the second case, notice that neither of our methods were called. In both cases, the methods inherited from object were called. That is because in neither case did we override those methods. In the case of 2-string, we added a parameter, so the signatures don't match. With the equals method, the problem may be less obvious. The equals method defined in object has, not surprisingly, a parameter whose type is object. So by changing the reference types, in the second case to object, our equals method is no longer a match for this call, because a parameter of type object will not be automatically coerced to the type length. As a confirmation that we did not override these methods, try adding the annotation override. You will notice that in both cases a compilation error will be generated. It is sometimes helpful to determine whether an object is a particular type. The instance of operator enables us to do just that. Before we explain this issue further, let's review the rules about typecasting. Upcasts, which involve assigning an object of a subclass to a reference of a superclass, are always safe, and therefore do not require a typecast. Downcasts, which involve assigning an object with a superclass reference to a subclass reference, must be explicit. That is because downcasts are potentially unsafe and risk a class cast exception at runtime. Here is where the instance of operator can be useful. By using the instance of operator to test whether an object is a particular type, we can ensure that downcasts are always safe. One should be very judicious in the use of this operator, however. It should not be used in place of dynamic binding. Doing so misses the purpose of inheritance and polymorphism. So now let's consider our third and final version of the length class. The instance data and constructor have not changed, so let's scroll down to the three instance methods. In this version, we are careful to be sure that we are overriding both methods. Notice the inclusion of the override annotations that confirm that we are. In order to override equals, the parameter had to be changed to be of type object. By making that change, we can no longer invoke the 2 inches method on it unless we downcast it to be type length. After all, the object class certainly does not have a 2 inches method. But before we do that downcast, we use the instance of operator to make sure the object passed in really is a length object. If it isn't, we return false, because if it isn't a length object, the two certainly can't be equal. For the toString method, we had to drop the ability to give the option on how a length would be converted to a string. Finally, we examined the main method we will use for this example. The only difference from the previous one is with the first 2 lengths, we no longer explicitly call toString. Let's run it to see how the output compares with the previous version. Notice that this time the output is the same for both cases. Because we are overriding these methods rather than overloading them, it does not matter whether the reference types are length or object. Dynamic binding is used, which uses the object type, not the reference type. We conclude with an explanation of the meaning of the reserved word final when it is applied to methods and classes. First, let's review the meaning of final in other contexts, beginning with its meaning when it is applied to primitives. When we include final in the declaration in that case, we are stating that the value cannot be changed. In other words, we are declaring a constant rather than a variable. When it is applied to a declaration whose type is a class name, the meaning is slightly different. In that case, its reference cannot be changed. There is no way to specify that the value of a mutable object is constant. Next, what about when it modifies a method name? In that case, it means that the method cannot be overridden. The object class has several final methods. These are methods whose behavior can never be changed. Lastly, let's consider the meaning of a class being labeled final. A final class cannot be extended. All of the wrapper classes, such as integer, are final classes. User-defined final methods and classes are also possible.